During this lesson, we're going to talk about testing a claim about a proportion. Previously, we've looked at how to write some hypotheses and some basic information about conclusions, and this time we are going to start putting this to work. So first of all, just reminding you of different letters. N is our sample size, or the number of trials, and it has been in the past. P is the population proportion, so that is probably going to come from a statement of what has happened in the past or what they think is happening in the future, but it's some sort of a percentage, most likely. But now when we have a particular sample proportion, not the population, when we're only looking at part of the subjects, then we have a sample proportion, and that is p hat. So this is where we're looking at an exact sample and saying that out of this many people surveyed or talked to or questioned, this many responded, and that's one way that it could come at us. And of course, Q is the complement of P, so if we knew our population proportion, we could just subtract to get the complement of it. I have a little note down here on the bottom right, p-value, and then this italicized P and p hat are not the same thing. So look closely at your symbols. P-value has to do with the probability that something is more extreme than alpha or more extreme than it's acceptable. P is the population proportion, and p hat is the sample proportion. Now within this particular lesson, we are going to be testing a claim about a population proportion. And I know that technically there are too many words on that slide. We're going to break it down later, but this is a way to get the key information we're going to look at again and again up there in front of us. So if you need to just pause the video, you may want to take a picture of that slide or pause it while you take some notes. We have to have several different requirements that we make sure are met before we even do this testing a claim. Otherwise, testing the claim simply doesn't apply. The method's not necessarily going to work. After we go through all of those things, then we can do the test. Once the test is complete, we want to form a conclusion. Now, we have stated this in the past, but again, we're going to be applying it in this lesson. So as we form conclusions, one little mnemonic device to help you is to say over and over and over till it's kind of programmed in your head, if the p-value is low, H sub O must go. So if the p-value is lower than our threshold, then we will reject the null hypothesis, which was H sub O. If we reject the null, that's not enough. You either have to go on and say there is sufficient evidence about the claim to support something, or perhaps you want to say we failed to reject the null and there is not sufficient evidence about the claim. But remember, we will never accept anything, so we either reject it or fail to reject it. Okay, let's see if we can apply this. After this page, we have an example coming up. And just keep in mind, we're going to have three methods that we're going to go through. One of them is the p-value method. Another is the critical value method. And a third is the confidence interval method, although we don't do that as often. The p-value method and the critical value method are equivalent. They will give you the same result. If your instructions tell you to use the p-value method, the critical value method will give you the same answer. If your instructions tell you to use the critical value method, the p-value method gives you the same answer. However, there are different numbers used, so you may have to do some different steps along the way. Just the conclusion is the same. We can use a confidence interval, but the confidence interval method may give us a different result. It may not, but it may. So down at the bottom, that last little section here, this is kind of a tip of the day. Only use a confidence interval to estimate a population proportion. Estimating it is different than testing a claim. So we can use a confidence interval to estimate the population proportion, but either use the p-value method or the critical value method for testing a claim. The only exception I would make to that is unless you are otherwise instructed. Now that would not come necessarily instructions from me because I would not choose to do that, but I do know that within this homework, sometimes it simply tells you to use the confidence interval method. So your confidence interval method is the one you should use. Be aware that it could end up with a different conclusion. So now is an example that we'll work through. As we go through this particular example then, first of all, let's just look at our key points here. We have 1,009 randomly selected consumers who asked if they're comfortable having drones deliver their packages. 54%, which was 545 of them, responded with no. Use these results to test the claim that most consumers are uncomfortable with drone deliveries. Now, we're not actually going to do the complete test on this page. We have another slide with the same problem written on it. But when we are going to test the claim that most are uncomfortable, what we're really looking at is a claim that more than half of them, and more than half then would be more than 0.5. And we're going to use a significance level of 0.05. Now, before we actually go through and do this, you want to look at all of your requirements. So as we go through that requirement check, is it a simple random sample? Well, it says right here, randomly selected, so I'm going to mark that one that yes. Is there a fixed number of trials? That's where we get our 1,009. So 1,009 is our fixed number of trials. So yes. Are these trials independent? It does not say that particularly, but there is no reason that one person being comfortable or uncomfortable should in any way affect the next person's response. So we can say that these are independent. One outcome does not affect the next. Each trial has two categories of success and failure. Success is whatever you're looking for. So if we're looking for to test the claim that most consumers are uncomfortable, then uncomfortable in this particular instance is going to be our success. And comfortable would be our failure, which might sound a little bit backwards, but at any rate, we've got two categories, so we have success and failure. The probability of success remains the same in all trials. Yes, we are always going to have the same possibility that they could say that. Nothing's going to change. We're not removing any cards from a deck or anything of that sort. So then you want to look at N times P and N times Q. And since these numbers just have to be bigger than 5, based on my sample size of N being 1,009, I am confident that N times P will be greater than 5 and N times Q would be greater than 5. And remember, my P is going to be not P hat, which by the way, 54% was P hat, but P that I'm testing is going to be 0.5, so like half of it. So in both of these cases, half of 1,009 is certainly greater than or equal to 5. So we've met all of our conditions, which means we can proceed with the test. Now this first part is the exact same problem. We've just gone ahead and written some extra stuff on here. Our claim that we are testing the claim that most consumers are uncomfortable. Most has to be greater than half. So we are testing the claim that P is greater than 0.5. Now remember, the claim could be your null hypothesis, or it could be the alternate hypothesis. In this case, it's the alternate hypothesis because it has that greater than symbol. And the null always has to involve the same number, but the null involves an equal. So here we have our claim greater than 1/2 or greater than 0.5, and then we have our null hypothesis of 0.5. Now we've got 3 different calculator screens that are put here just to remind you how to get to these. And I'll bring up a calculator and do this, but I want you to have this picture in front of you. So I'm going to bring up a calculator and we'll click Stat Test. And then under the test, we're going to go down to option number 5, which says we have one prop z-test. Now the one prop is because we have one proportion. The z is because we are using the normal approximation to the binomial, and we checked out that we can do that. So over here, if I make my calculator a bit bigger for us, I'm going to go to Stat, which is second row, third key over, or possibly if you're counting that top row, one more row down, third key over, and then we're going to go over. Notice it doesn't immediately come up. I need to go over to test and then down to option 5. Okay, now when I click enter, I get options that come up about p sub 0, x, and n. P sub 0, x, and n. Now let's look at how that compares to this particular case. My p sub 0 is my null, the p that goes with the null hypothesis, so it's 0.5. X and n actually come up here from these values in our sample. We had n of 1009 and we had x of 545. So that's where these numbers come from. This 0.54 is going to result on the next screen, but we don't enter that on this one. You have to have an actual x and n. When I very first opened my calculator, it did not show that I was testing to the right. It did not show this greater than. So it just came up here in the middle. I would have to go over, go down, and then go over to the test, which is greater than. I am testing that my actual one is greater than 0.5. Since 0.5 is p sub 0, that means I'm testing that it's greater than p sub 0. So when I do that, this screen is now exactly like this second one. I'm going to go on down to calculate, and then we will have a resulting screen that shows up on the next thing. So if I go down to calculate and hit enter, this screen is what is in that third picture of your calculator result. So the information we get here, first of all, what do these numbers need? Well, this is saying that we were testing the proportion. We were testing that the proportion was greater than 0.5. And that matches up with our original claim here. P is greater than 0.5. That's our test. Z is our z-score. We are going to use that on a later screen. But Z is telling you your z-score. So it's 2.55, and that z-score is your test statistic. Okay, test statistic. It is a result of the test. P is the p-value. There's no hat over it. And it's not our claim, this is just our p-value. So I've enlarged that here as well. P is 0.0054 approximately. This p-hat is the 54% that our problem already shared. So that gives me a level of confidence that I entered things correctly, but I didn't need that because it was already information that I knew, but that does tell me p-hat. And n is just repeated back to me. It was out of 1009. So I have all of these values. So what do we want to do with these values? Well, I'm going to take this last screen and it will show up for us again because it's the result of this test that we need to interpret. So here's the same problem, looking at it with the p-value method. Now remember, I said the p-value method and the critical value method give us the same result. They actually require the same calculator entry. It just uses a different number from the calculator in working on that. So when we conclude this, I have a little note here. Remember, if the p, which is p-value, is less than or equal to alpha, you reject the null. Well, that has to do a little bit with what that sketch would look like if we were to sketch it out. And this won't be perfectly done, but if we have our hill, and I know that alpha is just in the section to the right, because remember, if it were two-tailed test, we would need to divide that value by 2. But this is a simple one-tailed test, and we're going to use an alpha, as is typical unless you're told something else, of 0.05. So alpha is 0.05. Well, my p-value was 0.054. This p-value is smaller. P-value 0.0054 is certainly less than 0.05. And since it ended up over there in that tail is like the danger zone. It is dangerous to pull a cat by the tail. That is the danger zone. So if we end up over there, we need to reject the null. So our conclusion will be to reject the null. Now, if we reject, it is because there is sufficient evidence to say that that is not likely to be the same proportion. Now, always you're going to have to do two things in a conclusion. Either reject or fail to reject the null hypothesis. What was the null hypothesis? The null hypothesis was that the true proportion was half. We're going to say, no, the true proportion is not half. Now, why is that? We will reject the null hypothesis that the population proportion is half because there is sufficient evidence to support the claim that most consumers are uncomfortable with the drone deliveries. So we're going to look at this same problem again in the next couple of slides, but we're going to switch over, and instead of doing the p-value method, we will do the critical value method. Critical value method is going to be similar. Again, we're going to end up with the same information over here. But on the critical value method, again, this readout looks just the same. Instead of using the p, we're no longer interested in p, we're going to look at z. So when you look at z, critical value is this z method right here. And that's what I've rounded down here. That's the test statistic. Now this one I have kind of a pre-drawn little hill for us. What happens is that instead of comparing it to alpha, which we did before, we want to compare it to the z value that goes with that alpha. Now they're related. The critical value that corresponds to an alpha of 0.05 in a right-tailed test is 1.645. And if you'll follow this little arrow out, we've done this before. This happened when we were talking about the binomial distribution, but you get that critical value from second, vars, and inverse norm. If we go second, vars, inverse norm, which is option 3. Let me get my calculator where I can hit enter. Then I can say, okay, and again, we've talked about this before. If your calculator lets you choose the right tail, you can put 0.05 there. If your calculator doesn't have left, center, and right, you need to realize it's always going from the left. And if you're coming from the left, the area to the left is 95%, so I've put 0.95. So then we go and leave the mu and sigma at 0 and 1. Even if you've gone from the right, mu should be 0 and 1. And this 1.64 is right here. It's gone out one extra value, but you see 1.645, and that is what that would have rounded to, 1.645. That is your critical value. That's the value that cuts off that tail that has 5% of the area in it. Then we look at our test statistic. How does it compare to the 1.645? Well, it is to the right of it. So since this test statistic is in the critical area, which again is this tail, danger zone over here at the tail, since it's in the critical area, then we know that we should reject. That is the same conclusion we reached with the other method. Why are we rejecting? Because there is sufficient evidence. Now, what is there sufficient evidence for? Every time we are going to reject or fail to reject H sub O. But there is or is not sufficient evidence about the claim. So here we would say there is, and I'm going to scribble out is not, there is sufficient evidence to support, and I'm so sorry for this horrible handwriting, to support the claim. Now you're always supposed to restate this claim, but I'm just going to kind of point back up here. What was our claim? That most consumers are uncomfortable with the drone deliveries. So we have rejected the null because there is sufficient evidence to support the claim that most consumers are uncomfortable with drone deliveries. So we did the p-value method. P is less than 0.05, so we needed to reject the null, reject H sub 0 because we are going to support the claim. That's the exact same thing we get from the critical value method. Okay, we're going to look at the same problem, but we're going to look at a confidence interval method. Now remember, both the p-value method and the critical value method use the exact same calculator information and this same sort of wording. There is some additional wording on this one because we just want you to be able to see that in case you have a problem that asks you to do that. The thing is that right here it adds what your confidence interval is. You should get a percentage that corresponds to that. What that comes from is that unlike just having a one-tailed test, an interval is always in between two values. Since it's in between two values, that means we have some of the stuff over in the right-hand tail and some of the stuff over here in the left-hand tail. I could have changed those tails to be smaller so that that total was still 5%, but as we go through this in an effort to keep this side 0.05, then we've balanced that out with letting this tail be 0.05, which means the area in the two tails together is 10%, which of course is why in between here I will have 90%. Now on the calculator we start with the same options. We're going to go to stat test, but you're going to move right past option 5, which is what we used previously, and go on down to option A. It's still one proportion. The Z means we are still using a normal or normal approximation for the binomial, but instead of immediately testing that proportion, we're going to build an interval, so a confidence interval. Now these numbers come directly again from the problem, 545 out of 1009. My confidence level was given to me, so that's 0.9. I can bring my calculator back over just to show you again how to click that through so you can do it at the same time. So when we have our calculator here, I'm going to go to Stat, go to the right to get to Test. Underneath Test, I want to go down. Some calculators have more options than others, but I don't want that Z-test. I want to go on down and just keep going until I get right here to A, one proportion normal interval. Okay, that's really what that is. Then we'll hit enter. This is where you enter the numbers. Now on this particular one, I've worked it out for a different class or something, but we have 0.90. Then I go down to calculate. This is that last screen that you're seeing on this page. So again, we have p hat, which was given to us in the problem. That's the 54%. But these numbers are telling me what my interval is. What we are saying is that we are 90% confident that the true interval is between 0.51 and 0.57. That's like telling somebody, well, I don't know exactly what percentage is uncomfortable, but I'm 90% confident that the true percentage is between 51% and 57%. Well, you know, if your percentage is between 51% and 57%, both of those are more than half. So even here, as we conclude, since both of these were bigger than our h sub 0, then we're going to say we believe it is bigger than h sub 0. As it turns out this time, we are still going to reject the null because once again, there is sufficient evidence to suggest that it's greater than 1/2. Okay, so we're going to say the exact same conclusion here, but we don't always get the same conclusion this way. So don't use this method unless you're instructed to. Let's do one more. These examples are lengthy, I get that. A study of sleepwalking was described in Neurology magazine, and it included information that 29.2% of 19,136 American adults have sleepwalked. Would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? Use a 5% level of significance to test the claim. Okay, just kind of putting some stuff on here. This percentage right here that is given is our p hat, because this value came from our study. In the study, the N value, the number of trials, was 19,136. Fewer than 30% is what is being stated about the entire population. So this is what we're going to use as our P. Using a 5% level of significance, that is our alpha. So those are values we're going to use, but before we get to doing any of this, we need to check off. Is it a simple random sample? Well, since it was a study by Neurology magazine, you don't have all the information on this page, but Neurology is a premium research journal, and they will use a random sample. Fixed number of trials, 19,136. Trials are independent. If one person sleepwalks, the other one won't necessarily. Success or failure, they either will or they won't. The probability of success remains the same in all trials. So far as we know, the percentage is going to be what the percentage is. There's nothing that's going to change it, like taking a card out of the stack or something like that. N times P greater than or equal to 5, and N times Q greater than or equal to 5. Well, I have N 19,136, and I have P at 30%. So I can just easily pick up a calculator. 19,136 times my 30%. That's certainly greater than 5. And if this is P, then Q is 0.7. If I multiply by this by something larger, it's certainly going to be larger. The real issue there is if you have a very small number involved in your number of sample size. Okay, so we've got a requirement check. So now let's see what happens. If we are trying to look at whether or not fewer than 30%, then that fewer than 30% is what I'm wanting to claim. And this one then will be the claim. The reporter is claiming that fewer than 30%. That 30% then is what my null will be for my null hypothesis. My P for my null hypothesis, 30%. Once again, I have my values that I'm going to need. I kind of like this way of going through it because I don't have a lot of stuff I have to calculate ahead of time. I go to stats, test. This time I'm just testing the proportion, one prop Z test. My null proportion was 30% or 0.3. X is how many did do this, and if we look up here, oh dear, that value's not given. But I know that it's 29.2% of 19,136. So what I want to do is find out what X is. Bringing my calculator over again, I'm going to do my 19,136, and I'm going to multiply that by that 29.2%, so that will be 0.292. Now I know that they could not have possibly come up with part of a person that did sleepwalking. So while it looks this way, I want to use something reasonable. So that's where 5588 comes from. 5588. Oh, I moved the wrong thing over. So sorry. But 5588 came from me doing that. Now, if you don't round it off, you're going to get a slightly different answer, but you'd probably get a correct conclusion. But I just moved this to be a whole person then. And that again represents 29.2% of 19,136. Since my claim is that it is less than, I'm actually choosing this left-hand test then. And I hit calculate, and I get my values. Now remember, two different values are going to allow me to conclude this two different ways. First of all, I have the Z, and since this Z came from a test, this is the test statistic. P is 0.00796, which rounds off, as I have down here in the blue box, to 0.0080, and that is my p-value. So two different ways I can conclude this. And I think I have room to do this on the next screen. I think I've got the same problem there. So if I wanted to do it with the test statistic, that's the one that's here first. I know that my test statistic is negative 2.41. Well, the test statistic involves comparing that to the critical value. So again, you would have to think, okay, in my curve somewhere, I have a critical value that corresponds to my 0.05. Because remember, alpha is 0.05. First, we are testing a left-tailed test. So this area to the left is going to be 0.05. Okay, so my critical value is 1.64. 1.64. Now you might think, why did she do it again? We already knew it was 1.64, and this one's on the left, so it's negative. Well, this is true, but in case you run across a different value. So this critical value here is negative 1.64. My test statistic, oh, it looks like I'm lining that out, but negative 2.41 is way over here to the left. Negative 2.41 is in that critical region. It's in the tail. So we should reject. We need to reject the null hypothesis. Okay? So we are going to reject the null hypothesis. And we're going to say it's not really 30%. So does that mean that there is or is not sufficient evidence to say that fewer than 30%? Since we have rejected the null, we're going to support the alternative. And the alternative is that there is sufficient evidence to support the claim. And remember, the claim is that it was less than 30%. So we're rejecting that it is 30%, and we are supporting the claim. We believe that there's evidence to support the claim that it is less than 30%. And that is from the critical value method. The z-score that we get compares to our critical z, or our critical value. My very favorite method is the p-value method, because under the p-value method, I can then compare the p-value that I get from this result to my alpha. And since this is just a left-hand claim, it's just directly to alpha. So I see that 0.0080 is in fact less than 0.05. And remember, if it's less than or equal to, then we will reject and we'll get the exact same conclusion. Now the chances are that you are going to need to pause this video, kind of do it step by step, and look over and see what's going on. Please don't hesitate to use Ask the Instructor if you're in my class so that you can get some more direct help. I am happy to work with you. And if this all just seems a little bit mind-blowing, you will not be the first person that has shared that with me. Okay? I wish you the best. Let me know if there's something I can do.